Welcome everybody. In this video, I want to cover a handful of questions related to measures of variability, including calculating the range, calculating the standard deviation, and calculating the variance. And I'm going to use what you see in front of you here, which is Photoshop. It's going to allow me to draw using a stylus and also sort of solve the problems in real time so that you can follow along. One of the great things about this is you can pause the video when you need to and go at your own pace. But first I want to just direct your attention over here. You have the necessary formulas that might appear in problems related to variability. And essentially, I've tried to arrange them so that, generally speaking, the formulas on the left are for population data sets, and the formulas on the right are for sample data sets. The exception being these two formulas for the range. But let's get into it. So we have this first question. For the following population of n equals 6 scores, calculate the range assuming the data are discrete. All right, so discrete data is juxtaposed with continuous data, and we'll do a continuous data problem next. The first thing we want to think about is, what is discrete data? Well, that is data that has separate categories, where the categories are not fluid. They're completely separated by whole numbers or whole categories. And so, for example, this might be number of siblings. So you have to have a whole number. It's a discrete value. You can't have 1.3 siblings. You can have one sibling, you can have two siblings, and there's nothing sort of in between the whole numbers. So that's what makes this data set discrete. And you have two formulas for the range. This first formula is for discrete data, and you simply take the largest value, x max, and subtract the smallest value, x min. And so our range is going to be the largest value, which is 6, subtract the smallest value, which is 0, and we get 6. So fairly straightforward. Now, on the other hand, what happens if you get a problem that looks like this? For the following population of n equals 6 scores, calculate the range assuming the data are continuous. So, for example, maybe this is reaction time, how long it takes you to react to some stimulus. Because time is fluid, we call it continuous data. So for example, it might take you 1 second or 2 seconds or 3 seconds, but it could be any value in between those values. So 1.1, 1.2, 1.3, and any values in between those. So this, of course, means that we have to consider limits, real limits. This is something that is discussed in the module. It's also discussed in the textbook. But the idea is that we are essentially having these numbers, these whole numbers, be the representatives of the entire integer from a half a point below and a half a point above. So let me give you an example. This value of 2, if it's continuous data, 2 represents 1.5 to 2.5. So a half a point on either side. And thus, you can think about the formula for the range in this case as the following. Take your largest value, minus your smallest value, and then add 1. Because essentially you have half a point on the bottom that you have to account for and half a point on the top that you have to account for. So in this problem, the range is 6, the largest value, minus 0, the smallest, plus 1, the range is 7. So it's very similar, but the important thing to consider is taking note of whether or not the data are discrete or continuous. All right, so let's look at a new problem here. Let's get rid of these. And this one says, for the following population of 6 scores, calculate the variance and standard deviation. All right, so the first thing we need to note is that this is a population, and population formulas are over here. Next, we'll do a problem with samples, and you use these formulas, and we'll talk about the difference. But this symbol right here, sigma squared, is the symbol we're going to use for population variance, and this is population standard deviation. Note that they're only one step away from each other. Standard deviation is simply the square root of variance. And we'll talk about how to interpret them once we get there. But one of the values we need is SS, the sum of squares, and that's this formula right here. So I recommend doing the following steps when you have to calculate variance and standard deviation. The first thing I would do is list out the data points in a row, or excuse me, in a column. And let's solve for the population mean. So first and foremost, let's add them all together. The sum of all scores is equal to 18. And thus the mean is equal to 18 divided by 6, or 3. Okay, so the second step we want to do is create a new column, and these are known as deviation scores. In other words, how far each x value deviates from the mean. So our mean is 3 points. This first score of 0 is 3 points away from the mean. Specifically, it is 3 points below the mean. So 0 minus 3 is negative 3. 6 minus 3 is 3. 5 minus 3 is 2. 2 minus 3 is negative 1. 3 minus 3 is 0, and 2 minus 3 is negative 1. Now you can always double check your math because deviation scores should always add up to 0. And it looks like they do, so I'm just going to note that. Everything looks good so far. I hope you can read my writing. Using the stylus is somewhat difficult. It's somewhat awkward for me, so I'm doing my best here, but please let me know if you have any questions. So standard deviation is really our ultimate goal here, and you could define standard deviation as the average distance from the mean. So we want to know how spread out these scores are. That's variability. Well, average distance from the mean is, thinking about it this way, is how far each one of these values is from 3 on average. Now what we just did here is we calculated distances from the mean. That's what a deviation score is. So why not just add these together and divide by 6 to get the average? The problem is, again, that these add up to 0. And any time you divide 0 by anything else, it becomes problematic, and it's not what we want to be thinking about. So we're going to go around that by creating one final column. And this is what we take our deviation scores and we square them. And that's going to get rid of any negative signs. So negative 3 is this deviation score associated with the score of 0. We're going to square that value. So negative 3 squared is 9. 3 squared, 9. 2 squared, 4. Negative 1 squared. You get the idea all the way through. And now we have deviation scores squared. And we're going to add those values together to get something called SS. We'll explain what that means in a minute. Looks like we're getting SS equals 24. Again, 24 is the sum of these values. All right, so as you probably read in the module, hopefully, and also in the textbook, SS is the sum of the squared deviation scores. So that's exactly what we just did. We took the deviation scores squared and added them all together. And note, that is what the formula tells you to do for sum of squares. All right, so we're one step away from variance. Let's go ahead and calculate our population variance. We take our sum of squares, 24, and divide by n, which is 6. And that value is 4. So variance is 4 in this problem. Variance could be defined as distance from the mean squared, or I guess maybe distance squared from the mean. And the idea there that's problematic is we don't communicate in squared distances. So standard deviation is needed to be calculated, and that's simply the square root of your variance. So in this case, 2. Standard deviation could be calculated as, or could be defined as, average distance from the mean. In other words, on average, these 6 scores with a mean of 3 have a distance of 2 on average. So they're about 2 points away on average from the mean. That's what standard deviation tells you. It's a measure of variability, how spread out the scores are. Okay, so what we just did here is we calculated these values for a population of scores. Now let's look one final question, which is when you have a sample of scores. And what I wrote down here is the exact same question, except I'm turning it into a sample. So it says for the following sample of n equals 6 scores, calculate the variance and standard deviation. Now the only difference in your calculations is when you get to this final stage right here. Rather than divide SS by n, you divide SS by n minus 1. So let's go ahead and do that, and then we'll end this video talking about why we did that, the difference between n minus 1 for a sample versus just n for a population. So I'm going to, actually I'll use a different color, and let's use like a red. And what we'll do here is now imagine these are sample values. And so the first thing to consider is that the notation is different. We need to use sample notation. So all of these things I'm erasing are population symbols. And thus, let's just completely erase this. Thus, let's see, getting back into this with my sample values, let me just place them right here. So M is the value, the symbol we use for sample mean. M here, M here. And importantly though, this is what I was trying to get at here, is all of the math is exactly the same. Nothing changes here until we get to the variance. So for a sample, variance is calculated as SS divided by n minus 1. So in this case, it's 24 divided by 5. And grabbing my calculator here, that is a value of 4.8. And then let's go one more step and calculate the standard deviation, which is 2.20. So how'd I get that? Square root of 4.8, 2.20. So if you recall a minute ago, the population standard deviation in the question a second ago was 2, yet the sample standard deviation is 2.2. So when we considered these values to be a sample of scores, the standard deviation became larger, and that's because we divided by n minus 1 instead of n. Now there's much more detail about that in the textbook, but here's a brief sort of generalization of why we do that. Samples are typically not as variable as the populations that they come from, and that's simply because when you randomly select people for a sample, you're more likely to get people who are average, because there's more of them when it comes to normally displayed data. There's more people in the middle. So the people on the ends, the really variable people, are less likely to be included in a sample. So the problem here is that samples become underrepresentations of population variability. We need to make a correction for that. And so we do that by dividing by n minus 1, which is a smaller value, and that makes the end result larger. It's a general correction we make. It's somewhat arbitrary, like why n minus 1? And the reason is that if you took every possible sample of size n and calculated all the possible standard deviations and then averaged them, you would get the exact population standard deviation. So that last little bit is just a proof of why you do n minus 1 versus n. But I really want to harp on the idea that the calculations are almost identical to one another until you get to these last steps. All right, so those are some problems based on measures of variability.